And so it is that we start the first Lightrans webinar of 2024. The topic today is very exciting, as I'm sure you will all agree. It is a modelling and design of metastructures, of course in the context of the technology implemented in the optical modelling and design software VirtualLab Fusion. For those of you in the audience who are completely new here, VirtualLab Fusion is, again, an optical modelling and design software developed by the company Swarovski Photonics, and the general distributor of which is Lightrans International. And we're lucky enough to work with a wonderful team of distributors all over the world. The philosophy of VirtualLab, or behind VirtualLab Fusion in a nutshell, is that it allows its users to control the accuracy-speed balance, which is a compromise that is always on the table when we talk about simulation technology, not just in optics, not just where VirtualLab Fusion is concerned, but whenever we talk about simulation technology, that compromise between accuracy and speed is always there. And the way VirtualLab Fusion allows you to have this control of the accuracy-speed balance is by putting at your disposal a pool of interoperable modelling techniques on a single software platform. The fact that this integration, that this interoperability is done on a single platform is quite relevant, both in terms of the seamlessness that it lends to the process, but also because it prevents loss of information by changing from one mathematical model of the light to another. The integration, again, the interoperability is single platform. That means the model of the light is consistent throughout, and we avoid such loss of information as described when changing from one model to another. So the tagline that sort of wraps this whole philosophy up is that you can be as accurate as you need to be, while also ensuring that your simulations are as fast as possible. Before we actually delve more deeply into the topic of modelling and design of metastructures, I want to make a bit of a disclaimer, and it is that in this field, what we're going to be discussing here today is just the beginning of the story. This is a field, this is a part of our technology that we are developing, researching very strongly at present. And so this webinar must be understood as a summary of what is currently possible, but also as a bit of an announcement that a lot more is to come, that we are, again, developing very strongly here, and that we can expect great things to be released in the near future throughout the year, where this field of modelling and design of metastructures is concerned. So once again, we have a very strong starting point, as we're going to see, but a lot of new things, a lot of more powerful tools will be released in the future. And the last point, before we move on to the examples that we're going to be going through together, is to put the whole concept of metastructures in a bit of a wider context. So any design process can be divided into two separate parts. They can sometimes be more intertwined with each other when it comes to the actual work that is done, but in terms of understanding the problem, every design task can be separated into a functional design stage and a structural design stage. What we see shown on the slide now is the functional design stage, a pure mathematical abstraction of the function we want the component or system that we're going to design to fulfill. So in particular, what we're going to be focusing on throughout the webinar is we want our element, the element we're going to design, to realize a specific wavefront phase response. And what physical embodiment we come up with to realize this desired function, to produce this wavefront phase response is then the structural design stage of the process. And the answers there can be manifold. The figures use the particular example of a lens, but so in that case, but this is a more general overview. We can select a structural embodiment in the form of a freeform surface, a smooth surface, or a freeform surface that is segmented, or a diffractive profile, or, as is going to be the main topic today, a meta-surface. How would we define a meta-surface? The whole metamaterial, metastructure, meta-surface discussion is based on attempting to replicate a certain phenomenon that we see already in reality, but in a man-made form. So what I mean is, in optics, for example, we very often talk about the refractive index, but this is an emergent property, a bulk property that is actually, that can be traced down to a molecular, atomic, and even subatomic level of the structure of nature. And so this process of an emanating property by virtue of manipulating very small structures is what we want to replicate in a man-made form with metastructures. Of course, we don't go all the way down to subatomic level. We are still going to use materials that exist, which means we are at several scale levels above that. But the concept, the whole philosophy behind it, can be understood in that way. This takes us to the conclusion that we are going to be working with sub-wavelength structures in general whenever we talk about metasurfaces. And metasurfaces in particular mean that we're going to be working with flat components. So a certain arrangement of unit cells on a surface, on an aperture. Okay, so that's it for the more general overview part of the webinar. Let us dive right into the first example, which is the design of a two-dimensional, non-paraxial beam splitting metagrating. We see a description of a design task on this slide, and again, functional design. We want to construct an element that, when a monochromatic, more or less collimated beam of light impinges on this element that we want to design, that light will be split into a discrete set of orders that will take a 3x3 type arrangement. And the conditions that we put on the performance of this design is that we want the power distribution into these working orders, the 3x3 beams, to be as uniform as possible. And also we want to maximize the efficiency of the whole energy we put in the form of light in the incident beam split into the working orders, because there will be stray light in addition. So we want to maximize the efficiency, we want to maximize the power that goes into those 3x3 working orders, and we also want to ensure that the energy distribution among those 9 orders, 3x3 orders, will be as uniform as possible. That is more or less the functional design. And now we start taking baby steps towards structural design, because we are talking about generating a discrete set of working orders. We can very quickly conclude that the overall structure will in one way or another be periodic. So we're going to have a replication, a periodic replication of a fundamental period. Okay, now what happens structurally speaking inside this period is now the structure design, and we decide we want to use metastructures for the embodiment of this function that we want to realize. So the unit cell, we have to make some decisions at the beginning. We decide what materials we're going to use. The substrate glass is going to have a refractive index of 1.5, and we're going to use pillars with a circular cross-section, that is cylindrical pillars, whose refractive index is going to be 3.8, so very high. The period, so the size of the period of the metagrating, so that square that we can see in the top-down view there, will be fixed. That the size of that period and the pixelation characteristics will be fixed from the orders that we want, the angles involved in that separation into the 3x3 orders. So that will fix the angles. We're talking about a non-paraxial situation. That means those angles are going to be relatively large. And from that, the pixelation and the period is determined. So let us take a closer look at the functional design stage. To that end, we're going to use the IFTA, the Iterative Fourier Transform algorithm. This is a tool that is also provided with VirtualLab Fusion. And what the IFTA is going to provide is the phase distribution of the period that we need our nanopillars, our metastructure, to then realize with, in this case, a structure in the form of an arrangement of pillars with variable diameters. What we see on screen right now are 4 different results of that IFTA, of that Iterative Fourier Transform algorithm, per period. So each of them represents a possible period of our structure in terms of the phase function. Now, the engineer with these results, with a set of results, will select one of them. For example, this one, chances are that some of them will be easier to fabricate from the get-go than others. So we make an educated guess, we make an educated selection, and we say, okay, let's go forward with this phase distribution. This concludes the functional design stage of the process. And now we go to the pillars. So again, some assumptions are made. The materials are decided in a preliminary stage, as well as the pillar height. The height is going to be the same for all pillars in the structure, and we select this height together with the diameter, the pillar diameter range, and we do so in a way that guarantees an aspect ratio of the pillars that will not cause many problems, or that is reasonable, so to speak, from a fabrication point of view. So knowing the materials we're going to use, their refractive indices, we select a pillar height and a pillar diameter range to investigate. That provides a reasonable aspect ratio for the pillars. This part of the design process is a bit glossed over, but that is how we get to that pillar height that is already fixed there. What we do next is we analyze the response of the nanopillar structure as a function of the pillar diameter. So we set up for this stage, and there are sub-assumptions we make at this step. We're going to generate a regular grating where all the pillars are exactly the same. They all have the same diameter. And we're going to simulate that grating with all equal pillars and read from that simulation the phase and efficiency, amplitude of the working order. Because we're working with sub-wavelength structures, the working order is the 0th order. There will, in all likelihood, only be a single propagating order. So we read that information, and what we do is we repeat this process. We repeat several iterations of this process. We always have a regular pillar grating. All pillars are the same, but we change the diameter of those pillars from one iteration to the next. And for each iteration in this process, we store the phase and the efficiency of the working order of that 0th order. Okay, then we create from that information the curve, the plot that we see on screen that gives us a relationship between the efficiency and the phase, the response of the structure as a function of the pillar diameter. Of course, the assumption implicit here is that when we take those pillars that we simulated as a perfect grating with all pillars the same, when we take those pillars and put them in the pixels of the period of the metagrating, that the phase response, the phase and efficiency response we're going to get per pixel of our beam splitter is going to be more or less the same than the efficiency and the phase we can read in this plot, in this 1D plot. So that is an assumption. It is not a perfect assumption, but it is a very reasonable one that will at least provide us with a starting point that we can, of the design of the structure, that we can then at a later stage further optimize. And that optimization is something we're also going to take a look at here. So we have established this relationship, we have this starting point. And now, remember, from the previous step, we also have that result of the IFTA, that phase distribution that we want to realize. So we take this curve and we invert it. First, we extract the range that we're interested in. We want to focus on a pillar diameter range that provides a phase response that is as smooth, as linear as possible, that also covers the whole 2 pi radian range in terms of the phase. And in terms of the efficiency, we want the efficiency to be as high as possible and as uniform, as constant as possible over that range. Those are the conditions that lead us to select that particular range of pillar diameters here in this graph. So we extract this part, we see some screenshots from the user interface of VirtualLab Fusion, and we use a module that is a programmable feature in VirtualLab Fusion to invert this curve so that instead of phase as a function of pillar diameter, we have pillar diameter as a function of phase. And then we construct the period of our metagrating using the phase information that the IFTA delivered and mapping that to the different values of the pillar diameters using the curve that we generated previously. So that's what we can see here. Each pixel of the period as resulting from the IFTA will have a given phase value. We can read that phase value in the curve that we generated in the previous step and assign a pillar diameter according to that phase value for that particular pixel of the period. And of course then the structure will be a periodic replication of this metagrating period. Then we can simulate the structure that results from that initial pillar arrangement that we just generated in the way I described. For both steps, for the initial analysis in which we obtain the phase and efficiency as a function of pillar diameter, and also for this stage when we're going to simulate the metagrating structure itself, we use as a modeling technique the Fourier model method, FMM, also known as rigorous coupled wave analysis or RCWA. This method assumes periodic conditions, so that works perfectly well both for the preliminary analysis of the regular pillar grating from which we obtain the values of the phase, and for this step where we simulate the metagrating itself with the variable arrangement of pillars inside a single period. So by running the FMM on this metagrating, again what we see here on the left is a single period of that metagrating, of that pillar metagrating, we obtain the results that we see on the right of that slide. And what we see there are the 3x3 working orders of that metagrating, and we can read from the table the overall efficiency, which is close to 80%, that is already quite good. And also the uniformity error, both peak to valley 25.3% and root mean square, which is 16.9%, so around 20-30% uniformity error. That lack of uniformity can be seen in the different colours of the efficiency of the different orders in the 3x3, in the colour plot of the 3x3 working orders. So now we have a starting point from which we can perform a parametric optimization on this structure. So we take this metagrating and we perform a parametric optimization on it, where we maintain the pillar positions. Each pillar is centered in its pixel, and we take the pillar diameter as the variables for the optimization. And we want to maximize efficiency and minimize uniformity error. Those are the two curves that we see on the curve on the right there. Red is uniformity error, that's the curve that goes down. For those of you that have trouble perhaps making out different colors. So the curve that goes down is a uniformity error, and the curve that stays more or less constant at the top, that is the efficiency. And on this next slide, we see the result of that parametric optimization. From the colors of the orders, we already see that the uniformity is a lot better. The efficiency, the overall efficiency, has been maintained, increased a little bit, but for practical purposes, it has been maintained at about 80%, which is quite good. And the uniformity error has gone from 16, 17%, 25% to all the way down to the single digits, 3.4% in the case of peak to valley and 2.4% in the case of root mean square. So this illustrates the whole process, the whole workflow for the design of a beam splitting metagrating that has non-paraxial behavior. That takes us to the second example of this webinar, which is the design and analysis of a meta lens. And let's start by taking a look at the design task. We take a plane wave as our input field, monochromatic, wavelength 1550 nanometers, linearly polarized along X, and with an aperture diameter of 70 microns. And we want to design an element, in this case a meta lens, that will take this incident plane wave and focus it into a point 200 microns away. Now, from the focal distance and the aperture of that incident plane wave, we determine the numerical aperture, and from that we can again determine the pixelation characteristics of the meta lens. So we know how many pillars we're going to have to design in the nanopillar distribution of the meta lens for the given aperture. We make some preliminary decisions about the materials that we're going to use. Titanium oxide for the pillars, a refractive index of 2.4. The substrate glass will exhibit a refractive index of 1.5, and the shape of the pillars is going to be cylindrical. Important to mention here also is that the parameters of this example are taken from a published reference. You can see the citation there on screen, and of course it will be provided to you with a follow-up material of the webinar, so you don't have to write it down now. It will be you will find it in the webinar material later on if you want to read that more in depth. So we basically replicate the workflow steps of the design in VirtualLab Fusion. The starting point, the functional design stage of this example, is very straightforward. We know we need a spherical wavefront phase response, so we just generate that phase. We don't need something as complex as the IFTA as for the previous example. Here we know the phase distribution we need. So we generate that. We see some screenshots from the user interface of VirtualLab Fusion. We generate that ideal lens transmission function. We fix the aperture, we fix the focal length, the wavelength, and the sampling distance. That is the pixelation characteristics. And from that we obtain that phase distribution, that phase transmission, that phase response that we need to realize with our meta lens. The next step is pretty much the same as in the previous example. We perform a series of simulations with regular gratings where the pillars are all the same. They all have the exact same diameter, and that diameter is going to change from one iteration to the next, so that we can create that response curve of efficiency and phase. Again, as before, the pillar height is determined in conjunction with the refractive indices of the materials and the diameter range that we're going to envisage for the pillars, to ensure a reasonable aspect ratio for the pillars and to ensure that we will be able to fabricate the structure later on. In this case, unfortunately, we said previously that we want that phase curve to be as smooth as possible, as linear as possible. Here, that is not the case, unfortunately. We have a snag, a bit of a snag there, a resonance peak that sort of goes against those preconditions that we set on the phase curve, but we will be sure to avoid that little bit of a snag when we create the pillar distribution. And also another thing to mention here is that the whole 2π range is not covered exactly. We will come back to this later. Now, having that information, we once again use a C# module, that is this programmable capability in VirtualLab Fusion, to generate the pillar diameter distribution using the phase response that we want to generate and the phase information and efficiency information as a function of a pillar diameter. The module is provided with the other sample files of this use case, so it's just a question of running it, and out comes that distribution of pillar diameters as a result. This module already makes sure that we avoid that snag, that resonance peak, when choosing the pillar diameters. What we next look at, what we next analyze, is the response function of that pillar distribution we just designed. This means we're not simulating the meta lens itself, the meta lens proper yet. What this is simply mapping back, once again, from the distribution of pillar diameters that we just generated, back to the efficiency and phase information that we generated, that curve that we generated, and reconstructing the amplitude and the phase response, the complex response of this pillar distribution. And from that, we get what we see on screen right now. That complex valued response function of the pillar distribution we designed is on the left, amplitude and then phase. And then on the right, we see the deviation of this phase with respect to the ideal spherical phase distribution that we generated in the functional design stage. And we see some concentric rings in that deviation that is just the subtraction of one from the other. That is caused by the fact that I just mentioned, that we don't cover the whole 2π radian range of the phase with the pillar diameter range that we're looking at. So that's where those concentric rings come from. The next step is to build the meta lens. So we take that pillar diameter distribution and we create a structure out of it. We create that meta lens distribution, that pillar distribution that is going to be the physical meta lens. and we can take a look at that distribution of the pillars, and we can see how that pillar distribution mimics the behavior of that phase response, that wavefront phase response function that we want to elicit. So we can make it out a similar structure, which is to be expected because of the way in which we constructed this pillar distribution using a mapping from the phase we wanted to the pillar diameter. So we also see a mapping in the pillar distribution itself. Next, we simulate the interaction of the incident field with that meta-lens, with the actual physical meta-lens structure, and we generate the complex transmission function of that meta-lens. So this is actually the field, just the phase here, but we calculate the amplitude as well. This is the transmission function of the meta-lens itself, of the structure of that pillar distribution that we just defined. And we can also take a look then at the focal spot that is generated if we propagate that complex transmission function into the focus, into the focal plane, and we can again take a look at that PSF, at that focal spot, in this case the intensity. And we can compare all three results, from the ideal result of the functional design step that is on the left there, a perfect area. Then in the middle, the response of a pillar design. We see it is pretty much identical to the ideal situation. So those concentric rings that come from the fact that we don't cover the whole 2π range really don't have much of an effect. We cannot see it here in the focal spot. And then finally on the right, we see the focal spot of the meta-lens proper. And we see that in this case there are some slightly stronger secondary maxima in the case of the meta-lens itself. So the actual propagation through the pillar structure causes some aberrations. There can be, so the assumptions we make when we construct that pillar distribution, assuming that we can extrapolate the phase and efficiency response of the individual pillars from simulating a regular pillar grating and extrapolating that into a situation where we do not have that regular pillar grating anymore, but a different arrangement of pillars. This assumption appears to fail slightly, not very much, but there are some discrepancies with the ideal case. That could be the reason. The fact that this assumption is not perfect. So maybe this initial distribution of pillars would lend itself to further optimization, as we saw in the previous example with a beam splitter. Finally, it's also worthy of mention that we can export the pillar distribution from VirtualLab Fusion for further or for subsequent fabrication of the structure. With that, we conclude this presentation. I hope you found it interesting. I hope I managed to impress upon you that we are already capable of so much in this field, but also that there are a lot of exciting new things coming in the near future and to look out for them. And now that's it from me. That's it for this presentation. Thank you for listening, and let's open the floor to your questions.